Radicals can be classified as primary, secondary, and tertiary according to the carbon that bears the unpaired electron. If the unpaired electron is present on a tertiary carbon, then it's called a tertiary radical. If it's present on a secondary carbon, then it's called a secondary radical, and so on. The alkyl groups stabilize radicals the same way they stabilize carbocations, that is by hyperconjugation. So here is the correct order of stability of the radicals. You can see that the tertiary radical is more stable than the secondary, and then comes the primary and methyl. Regioselectivity of radical substitution reaction. When butane is subjected to chlorination in the presence of heat or light, you can get two different products. Replacing one of these hydrogens from the primary carbon is going to result in the formation of 1-chlorobutane, whereas replacing the hydrogens from these secondary carbons is going to result in the formation of 2-chlorobutane. But what is the relative amount of these two different products? According to statistical distribution of the products, we may expect 60% of 1-chlorobutane and then 40% of 2-chlorobutane. Why 60% of 1-chlorobutane? You can see there are 6 hydrogens that can be replaced to give 1-chlorobutane, whereas in the case of 2-chlorobutane, there are only 4 hydrogens which can be replaced with chlorine to give the compound. But when the reaction was carried out in the laboratory, the products are found to be 29% of 1-chlorobutane and 71% of 2-chlorobutane. This definitely tells us that the product distribution does not depend solely on the probability of a chlorine radical colliding with a primary or secondary hydrogens, but there is something more than that. Here is the most important information. We already know that the tertiary radical is more stable than the secondary, and then comes the primary. But what is the relative ease at which these alkyl radicals are created from chlorine radical? After experimentally determining the amount of each chlorination product that is obtained from various hydrocarbons, scientists were able to conclude that at room temperature, it is 5 times easier for a chlorine radical to form the tertiary radical than the primary radical, and it is 3.8 times easier to form a secondary radical than the primary radical. A bromine radical is more selective than a chlorine radical, where in this case you can see that the tertiary radical is formed 1600 times easier than the primary radical. So the relative amounts of products that is obtained in an halogenation reaction is based on two important things. One is probability, which is basically the number of hydrogens that can be substituted. And the next one is the reactivity, which is the relative rate of formation of a particular radical. So if you want to determine the actual amount of products that will be obtained in the reaction, in the halogenation reaction, then you have to multiply probability and reactivity. So using this, let's find out what is the anticipated percent yield of each of the alkyl chloride in this reaction. So for 1-chlorobutane, if you're going to take 1-chlorobutane, there are 6 hydrogens that can be substituted by the halogen. So the number of hydrogens here, which is basically the probability, is going to be 6, and if you're going to multiply it by reactivity of the primary radical, because when you replace one of these hydrogens in here, it's going to create as a primary radical, and the reactivity of the primary radical is 1.0, and we are going to multiply this together, and this value is actually 6. And similarly for 2-chlorobutane, this number is actually going to be 4, because there are 4 hydrogens that can be substituted for the chlorine, and the relative reactivity of the secondary radical here is going to be 3.8, because when you remove that one of these hydrogens, that's going to create as a secondary radical, and when you multiply these numbers together, it's going to be 15. So on the whole, the total amounts of all the alkyl chloride products that is obtained here is going to be 21, which is going to be 6 plus 15. That's going to be 21. So now if you want to determine the actual amount of each one of this product that is obtained, then you have to divide this number by the total amounts of the alkyl chlorides that's formed. So here in this case, it's going to be 6 divided by 21 times 100, which is going to be equivalent to 29%. And in this case, it's going to be 15 divided by 21 times 100. That's going to be equivalent to 71%. So this is the total amount of the two different products that are obtained in the chlorination of butane. And again, you can apply the same thing here for finding the relative amounts of products that is obtained in the bromination reaction. But remember, a bromine radical is more selective than a chlorine radical, where the secondary radical is created 82 times much easier than the primary radical. Now, when you apply the numbers in the formula, these are the numbers that you're going to apply. So again, let's go find the relative amounts of the products here. So we have 1 bromobutane and we have 2 bromobutane as the products. So here there are 6 hydrogens and the relative reactivity of the primary radical is going to be 1. So that there is no change in that. But here there is still going to be 4 hydrogens, but then the relative reactivity of the secondary radical has now increased, which means it is 82 here. So when you multiply these numbers, then it's going to be 6, and here it's going to be 328. To determine all the alkyl halides, alkyl bromides that is formed from this reaction, you have to add these two numbers here. So when you add 6 and 328, it's going to be 334. And to determine the percentage of one particular product that is being obtained, then you have to divide that number by 334 times 100. So when you divide the numbers, it's going to be giving you 2% here, and in this case it's going to be 98%. So let's do the math here. If you do it, it's going to be 98%. And you can see how selective the bromination is, where it predominantly forms one particular product. Now we need to ask ourselves why a bromine radical is more selective than a chlorine radical. In order to answer this question, we have to look into the delta H for the formation of primary, secondary, and tertiary radicals by a chlorine radical and also by bromine radical. Here is the delta H for formation of the radicals, where you can see that the chlorination is exothermic. This is an exothermic reaction, whereas this is an endothermic reaction. So this is the chlorination is an exothermic reaction and the bromination is an endothermic reaction. That's the very first information that we have here. Now we also need to remember that bromination is a much slower reaction than chlorination. Why? Because if we look into the activation energy for the removal of hydrogen from alkane molecule, we can see that for bromination, the activation energy is about 4.5 times much greater than the one that we have for chlorination. So on the whole, bromination is a slower reaction, whereas chlorination is faster. Here is the third piece of information that we can have from the reaction coordinate. We know that chlorination is an exothermic reaction. We also know that, according to Hammond's postulate, that the energy of the transition state in an exothermic reaction is going to be looking more close towards the energy of the reactants. And you can see there is not significant energy difference between the activation energy for the formation of the primary, secondary, and tertiary radicals. But in the case of bromination, we know that it is an endothermic reaction. And in an endothermic reaction, the energy of the transition state is going to be looking more close towards the energy of the products, and you can see there is significant difference in the energy of the products, right? Because of which we can expect there is significant difference in the activation energy for the formation of primary, secondary, and tertiary radicals. So we can conclude that a chlorine radical makes primary, secondary, and tertiary radicals with almost equal ease, whereas a bromine radical has a clear preference for forming the easiest to form tertiary radical. Or in other words, we can say that the bromine radical is relatively unreactive and selective, whereas chlorine radical is very reactive and it is non-selective. And this is called as the reactivity selectivity principle, which states that greater the reactivity of the species, less selective will it be. And since chlorination is relatively non-selective, it is only useful when all the hydrogens are same. Here is cyclohexane and all the hydrogens in here are exactly the same. And therefore, when you do the chlorination reaction, you get only one product. But if I'm going to take a compound where there are different types of hydrogens, then it can lead to more than one product. Why there is only chlorination and bromination and not fluorination or iodination? The relative reactivity of the halogen radicals is going to follow this particular order, where the fluorine is the most reactive of all the halogen radicals and iodine is the least reactive. The fluorine radical is going to react readily with alkanes to form the alkyl radical, and this alkyl radical is also going to react rapidly with fluorine to give the alkyl halide. And both of these reactions are exothermic. And in contrast, if you look into the iodine radical, it is the least reactive of the halogen. And in fact, it is very unreactive, that it is unable to remove the hydrogen from the alkane molecule. And you can see that this is an endothermic reaction, right? So on the whole, the fluorine radical is very reactive, more like an explosive reaction, whereas the iodination is super slow, that it doesn't happen at all. So therefore, we only have chlorination and bromination happening.